Alright, guys. Welcome back to another episode of Firing Solution Friday. I'm Grant, and you're watching Recreational Sniper. So, in this episode, we're going to look at our 944 yard shot that was made using 16-inch 308s. So in this episode, this is actually going to be a two-part deal. This first part is going to be with my rifle, because my scope setup is different than Garen's. Mine's in mils, his is in minutes of angle. And I'm using different ammunition than he is. So I'm using the 185 grain Burger Juggernaut, loaded in by Federal Premium Gold Medal Match. So it's store-bought ammo, and he's using the 168 grain Hornady ELD match ammunition that was store-bought. So in this episode, we're gonna just focus on the figuring out the firing solution for my rifle, and in the next part of this episode, part 2, I will release next Friday, and it'll be on Garen's rifle, which is a Remington 700 Tactical 308 with a 16.5 inch barrel. Mine is a Ruger American Tallow exclusive. I've been calling it the Ruger American Tactical, and it is a 16.1 inch barrel 308. So, getting started into this, we got to first establish how we're shooting and where we're shooting and all that. So we need to know things like the target altitude, our firing position altitude, which has to do with the barometric pressure. And there's a couple of ways that I like to figure that up. One of the ways I like to figure my altitude is with a GPS, like this Rhino 755T. Of course, you don't necessarily have to have that model GPS to do this. And I also like to use a Kestrel. Now, I don't have this cool fancy Kestrel that does the ballistic calculations for me, and that's the reason why I'm doing all these firing solutions on my own. So you see, I just have a regular Kestrel 5000. There's no ballistic software in here. And then a third thing that I like to use is Google Earth or Google Maps. Typically use more Google Maps than I do Google Earth. But with those three different devices put together, use Google Maps in pre-planning. So I know the general area where we're going to set up at, and if we pick out a spot that we're going to set up a target and pick out a spot that we're going to set up a firing position, then I can use Google Maps and I can pre-plan most of my firing solution that way. I can get the altitude, and then when I get out there, I can verify the altitude with the GPS and verify the barometric pressure at that altitude with the Kestrel. Okay, so we want to get as much information as possible, and so that's how we did it. Now, particularly this past weekend when we did the 944 yard shot, I actually did not use the Kestrel. I don't know why, I just didn't think about it. So we're going to go off of just GPS altitude, and that's about it. That's all we're going to go off of for this, because we kind of set up this shot without actually pre-planning it. So the target altitude ended up, according to the GPS, the Garmin, ended up being, let's see, target is going to be T, and that was at 654 feet in elevation. And then our final firing position, our FFP, was at 515 feet elevation. So we are shooting uphill slightly. Now, over the course of 944 yards, and the difference in altitude is not all that much. Let's see, turn the calculator on. We'll take 654 and we will subtract 515 from it. So we're at a difference of 139 feet over the range of 944 yards. So basically, like this would be 944 yards, and this would be 139 feet. So it's important to note that we used our rangefinder to get our yardage. We didn't actually use the GPS. I did measure the distance with the GPS, but I don't have it set up really to give me the distance in yards. And if you were to use and pre-plan like we normally would and use Google Maps to get your distance pre-planned out and set up based on coordinates you took out in the area, in the scouting process, your Google Maps and Google Earth range is always going to be a horizontal range. It's going to be just the horizontal range across the Earth. Okay, same thing with the GPS. If you use a GPS, it's just going to give you a horizontal range. It's not going to give you a true range. Your true range is going to be different than your horizontal range. Your hypotenuse is your true range, and your actual horizontal range will be the base. So, of your firing triangle. So, when you're calculating your bullet drop, you mainly want to focus on your actual horizontal range, which is the reason why I always have my rangefinder set up in a way that it gives me the actual horizontal range. So that cuts out from me having to convert true range to actual horizontal range. So ideally I would use the GPS and then also use Google Maps to get, and kind of make sure that my actual horizontal range, everything, like the two different systems are agreeing with each other. And if they're not, if there's a big discrepancy, then I may have a problem somewhere, like maybe low batteries in the rangefinder or whatnot, or maybe I got one of my coordinates a little off. But anyways, you will need to know your true range for your atmospheric variables, because the bullet is actually still traveling through that much of the air. It's going from this point to this point, but gravity is only affecting it by this much. So being that it's only 139 feet difference in altitude at that range, where you're at a very, very small angle of upward shooting, and we were shooting under 1,000 yards, so I didn't feel that it was really necessary to calculate and do any other adjustments. So we just went off the actual horizontal range for this distance. Alright, so we know what our altitude is for our firing position, and that is basically how we're going to calculate most of this stuff. Now we're going to take a look at our charts here. Let's see. Get some of this other shit out of the way. Alright, so we're going to take a look at these charts. This first chart is our 0 foot in altitude chart, okay? And we're guessing that 2992 inches of mercury is accurate, but we don't exactly know. And see, and I wish I had taken the time to use the Kestrel when we were out there and got the actual barometric pressure, because that would have made interpolation a little more accurate than the results that we got. But then again, that's just one of those things. You got to get used to using all of this equipment if you want to make really, really precise firing solutions. All right. So we're going to start with this chart, and we're going to look at our 900 and 1,000 yard range. And the reason why is because we're shooting in between those 2 points. We're shooting at 944 yards, right? So let's keep that in mind, that our range is 944 yards. All right. So we had target altitude, firing position altitude, and actual horizontal range. It's 944. So we're going to take here on this sheet where it says at 900 we are come up as -10, which would mils. So we need to come up 10 mils, and for 1,000 we need to come up 12.1. So what we're going to do is we're going to take 12.1, we're going to subtract 10, we're going to get 2.1. All right. Now, there's a little more that goes into this because okay, well, we can just start with this. Okay. So we're just going to start with this, make things a little bit easier. We'll make it more complicated as we go. So we're going to get 2.1, right? And that's the difference between 900 and 1,000. So we need to figure out where 944 fits in there, all right? So 44 yards is basically like there's a 100-yard difference, right? And we're 44 of that 100 yards further than 900, but we're 56 yards shorter than 100. So what we would do is we would multiply 2.1 by 0.44, and we will get, this is where your calculator comes in, convert to decimal, we would get 0.29 or 0.924. 0.924. And you don't necessarily need this many value placements here, but then you would take 0.924 and you would add it to 10 because that's 44% of the difference, and you would add the difference back to your low number at 900 yards. So 0.924 plus 10 equals 10.924 mils, and that would be for 944 yards at 0 feet in elevation, right? So this is for our 0 foot in elevation chart, this chart here. Okay, so we interpolated that for 0 feet. Now we need to do the same thing for the next barometric pressure zone, which would be 29 inches of mercury even, and which would roughly be 899 feet, given that sea level is 2992. Okay, so we got to look at the same thing. Our 900 yard mark is 9.8 mils of adjustment, and our 1,000 yard mark is 11.8. So we would take 11.8 minus 9.8, and that equals 2. And then we're going to take 2 times 0.44 again, and I believe that is 0.88. Whoop. Sorry, guys. So 2 times 0.44. Yep, I was right. 0.88. And then we're going to add 0.88 to 9.8. Again, the low number there, so plus 9.8 equals 10.68. So we got a difference of we got a little bit of a difference in numbers here. So we're going to go ahead and scratch off this 0.4 and just round it down. So we got 10.92 and 10.68. So we got your 0 elevation, which I'm just going to go write that over here. It's your 29.92, 0 feet, and this is 29,899 feet. All right. So now we've got to figure out what our drop is for 515 feet. So this part's actually pretty simple. All right, we're going to clear that. We're going to take we're going to clear that. We're going to take our elevation that we measured out in the field, 515 feet. We're going to divide it by the maximum, our 29-degree chart, which is our higher elevation chart. We're going to divide that by 899 feet. And we are going to get 0.573%, basically. All right, so 0.573. Well, actually, it'd be 53%. So I'm just going to go ahead and write this out. We're going to take 515. We're going to divide it by 899, and we're going to get 0.573. All right, which is representative of 57.3%. Okay, so now we're going to take 10.92 and we're going to subtract 10.68. Hang on, 10.92 minus 10.68. Why is my calculator not working right? That keeps messing up the button. 10.92 minus 10.68. And we're going to get a difference of 0.24. So we're going to take 0.24 and we're going to multiply that by 0.573. And we're going to get 0.138. All right, which we can round up to 0.14. So we don't want to make this too crazy. All right, so we're going to take 0.14 and we're going to add it to 10.68. So 10.68 plus 10.68 plus 0.14 equals 10.82 mils. So really 10.8 mils is our solution, and that is our solution for 944 yards at 515 feet in altitude. That's how you get that drop, okay? So now we know how much we need to come up by. All right. So from there, we can decide. It's up to you whether you want to do the spindrift. I believe would be important at this point, but Coriolis effect is barely starting to matter. We could go into that if you want to, but more importantly, the spindrift, we need to go ahead and do that. So for spindrift, we're going to have to interpolate a few other things here. We're going to have to interpolate our time of flight, and we're going to have to interpolate our gyroscopic stability factors for both of these altitudes and then convert them to the altitude we're shooting at, okay? So we can get us an accurate spindrift calculation. So, going back to our zero elevation chart, we'll go ahead and do it first, keep everything in order. At 0 feet in elevation, we have a gyroscopic stability factor of 2.07, and at 899 feet, we've got a 2.13, okay? So we're going to do the same thing here. We're going to put 2992, 0 feet, so we know what we're doing, and that is 2.07. So if you might have noticed, as you go up in altitude, your gyroscopic stability factor increases. So the stability actually increases. 2900, 899 feet. It's 2.13. Okay. So we're kind of going to do the same thing here. We're going to take 2.13, subtract 2.07. We get 0.06. Okay. Now, this is one of those things where we're going to use actually this 0.573 again, because that's the altitude we're wanting to adjust this to. So we just simply multiply that by 0.573. And we get, so we go 0.06 times 0.573, and we get 0.034. We're not going to go further than that in decibels. It's just not really, there's really not much of a point to do so. Even if we did round up the 8 onto that 3, it would just be 344, which we could just take the 4 off the end. So there you go. And then we're going to take that 0.034 and we're going to add it back to 2.7. So 0.034 plus 2.07. And our corrected gyroscopic stability factor is going to be 2.10. So 0.034 plus 2.07 is going to be 2.10, because we're going to round that 4 down. Alright, so this is going to be our gyroscopic stability factor for 515 feet in altitude. Now we've got to fix our time of flights. So the time of flight scenario is going to be just about the same as doing the difference in mils. Pretty much the same math, just different inputs. So at 0 feet, we've got a time of flight at 900 yards. 900 yards is going to be 1.518 seconds. And at 1,000 yards, it would be okay, yeah. So at 1,000 yards, it's going to be 1.761. Okay, so what we're going to do is we're going to take 1.761. We're going to subtract 1.518, and we're going to get a difference of 0.243 seconds. Okay. And then we're going to add that back to our low number. So we're going to take 0.243. Actually, I screwed that. We are going to take 2.43 and multiply it by our distance of difference, which was 0.44 again. So times 0.44, I'm kind of tired. It's been a long week, so I'm kind of messing this up a little bit as we go, but we will get there. 1.07. So, or sorry, 0.107 is what it would round to. So we're going to take that 0.107 and we're going to add that back to 1.518 seconds. So 0.107 plus 1.518 is 1.625 seconds. Now that is for 0 feet in altitude for 944 yards. Okay, now we've got to do the 899 foot area. So our 29-inch mercury, or 899, again, given that sea level is 29.92. And we're looking at, for this here, we're looking at 900 yards at 1.501 and 1,000 yards at 1.737. So we're going to take 1.737, subtract 1.501. So we're going to 1.737 minus 1.501 is going to equal 0.236 times 0.236 times 0.44, and that's basically 0.104. All right, and then we're going to take 0.104 and we're going to add that back to 1.501, which is going to be equal to 1.605. All right, so that is now our 944 yard time of flight for 899 feet. So now we just got to take the difference of the two, multiply that by our 0.573 again, and then add it back to the low number. So 1.625 minus 1.605 is going to be 0.020, right? Just to verify. Yep, 0.020. All right, now we're going to take 0.02 times 0.573 equals 0.012. We can round that up. We can go 6, round that up to 5, round that up to 2. So 0.012. And then we're going to take 0.012 plus 1.605, and that's going to equal 1.617 seconds. That is for 944 yards at 515 feet in elevation. Okay, so now we can actually calculate our spin drift. Now that we've got our gyroscopic stability interpolated, and we've got our time of flight interpolated. I guess, again, it's important to note that none of this is going to be like 100% the most accurate. Of course, the only way to make it more accurate is to get better input variables. So it would have been better if I would have done my altitude actually check the barometric pressure out there, because different weather patterns actually cause variances in barometric pressure, and so you can't really go off of a barometric pressure at altitude calculator. Different parts of the world, sea level is not always 29.92 inches. It can vary a little bit. So anyways, let's get into spindrift. So on my charts, I actually like to keep some of this information down here below. So our spindrift formula is this little guy right here. You guys can pause and take a look at that if you want to. Alright, so moving on. We're going to calculate our spindrift out, and then we're going to convert it to mils. So 1.25 times our gyroscopic stability factor, which we corrected to be 2.10, plus 1.2, and multiply that by our corrected time of flight, which is 1.617. And that's going to be raised to the power of 1.38. No, 1.83. Sorry, I got it backwards. Glad I caught myself. 1.83. Okay, and that is going to give our drift in inches. So, we're going to take 1.25, multiply, parentheses, 2.1 plus 1.2. Close parentheses, times 1.617, and we're going to raise that to the power of 1.83, and we are going to get 9.93947 inches. So we're just going to say 9.94. 9.94 inches. Now we need to convert inches into mils so we can actually index it in our scope. Alright. So, at 100 yards, 1 mil is 3.6 inches, right? So, at 944 yards, we are going to need to do 3.6 times 9.44, right? And that will give us 1 mil at 944 yards. Oop. Fat fingered it there. 3.6 times 9.44, which is going to be 33.98 inches is 1 mil. That's 1 mil at 944 yards. So our drift is 9.94 inches. So basically we got to figure out how many mils that is. So we're going to take 9.94 and divide that by 33.98. And we are at 0.2925 mils. So 9.94 divided by 33.98 equals 0.293 mils. So we would round this up to we would index it to 0.3 mils. So 0.3 mils. So 0.3 mils of spindrift. So we're right at 10 inches of spindrift there at 944 yards, given the particular ammunition and particular rifle that I am shooting with its particular rifle twist and that sort of thing, plus the particular altitude that we're at. That is our spindrift correction. So, and being that we are in northern hemisphere, our spindrift deflection is always going to be to the right, so we need to correct back left. So we would correct left 0.3 mils. Alright, and that's just for spindrift. One thing, again, I'm not really going to mess with much because we lucked out. If you watch the previous video of us making the shot, I mentioned a couple times that there was really no wind. To be honest, we've gotten really fortunate and been really lucky the last few times we've gone out and shot in that we haven't really had much wind at all. Like, I mean, you could barely feel it. It's not even moving the grass for the majority of the time. So the wind is like likely 1 mile an hour or less. So it's extremely hard to correct for that. And even at 944 yards, 1 mile an hour wind can push the bullet a little off, but it's going to be so hard to correct for that. Like, for instance, we can just take a look here. If we use a 10 mile per hour full value, like a 90 degree, like a 3 o'clock or a 6 o'clock wind, full value wind, or sorry, 3 o'clock or a 9 o'clock wind, which would be full value, at our distance, it would either be 2 mils or 2.4 mils. So if we're using a 1 mile per hour wind, that's 1/10 of that. So we were talking 0.2 mils, so just 2 clicks of wind depending on direction. And for the most part, the wind we were getting was either coming right at us or coming from behind us. We weren't getting really any crosswind. So there really wasn't anything to correct for as far as wind goes. I guess we just haven't found a spot yet that's going to give us a bunch of wind that we really need to correct for. And as far as the Coriolis goes, we could correct for that. But I've already got an example here done for Coriolis. And even at 1,000 yards, the vertical Coriolis, the horizontal Coriolis correction is going to be like not even 1 click. It comes out to 0.07 mils. So you could click it or not click it, and it wouldn't really make that much of a difference. And the vertical Coriolis is based on the azimuth of 30 degrees, which the azimuth we're actually shooting on is 316 degrees west-northwest. But the vertical Coriolis there would be at 1,000 yards would be 1.87 inches, so not even half a mil. So even at 1,000 yards, it's not really worth adjusting for it. You could, but like I said, 1,000 yards is just the beginning point of needing to actually adjust adjust for vertical or horizontal Coriolis effect. So you could calculate for it at any distance if you wanted to, but you would just get some, like at 100 yards, you would get some incredibly tiny number that, you probably couldn't measure with a caliper or something. But anyways, if you got questions and comments, I'd like to invite you guys to leave those in the comment section below. If you would like to see more of this content, please let me know. I enjoy doing these things. I love the science of it and the math of it almost as much as I actually love shooting. And one thing I noticed too this past weekend is I actually enjoyed spotting more than shooting. Actually watching Garen shoot and watching the bullet trace and stuff. I had a really good time. I really enjoyed doing that and can't wait to get out there again. Hopefully we can set up for a longer shot. I know he was really, really wanting to dig into 1,000 yards, and we thought we had set the target up in the right location, and then from where we were going to shoot from, we did some rough estimations and some rough ranging with the rangefinder, and we ended up being 56 yards short of our goal of 1,000 yards. So next time we go out, we know that, and if we decide to set up in the same position, we can easily push the target back another 50 or 60 or maybe even 100 yards further, just to make sure we get that 1,000 in. There is another section that I'm really wanting to try to set up a 1,900 yard shot on for the 6.5 PRC, but that's going to be a process. It's actually, one area is easy to get to, but where we would have to set the target up is we would end up, making a 6 mile hike to get the target there. So, and back to get the target there and back when we got done shooting. So that's one of those things I'm working on planning, trying to figure out a way to make it easier, but you never know. We may end up just having to hike the whole thing, but like I said, there you go. That's our Firing Solution Friday for our 944 yard shot with 16-inch 308s. Next video will be a firing solution for Garen's rifle because he's using a minute of angle scope, and his is going to be a little more interesting because he run out of vertical adjustment long before he even could get to the target, so he was actually having to hold over, I think, like 9 minutes of angle. So it's pretty interesting, pretty cool, because he was actually able to get on target and stay on target for a few shots, which was really awesome. So like I said, thank you guys for watching, and we will see you next time in the next video. Peace.